Hello everyone and welcome to lecture. Today we're going to be talking about the multivariable limit, or the limit of a multivariable function. We'll also be talking about the continuity of functions and how the continuity of multivariable functions depend on the multivariable limit. So the idea is that we're going to start with talking about the informal definition and kind of move into formally what it means to take a limit. So the informal definition of the limit is very similar to the definition of the limit for single variable functions, the informal definition. The idea is that the limit of a multivariable function is the value the function approaches from every direction, or along every possible path. Of approach. So we'll talk about the exact mathematical definition of this, how we define this mathematically, and then go over a couple examples of how we calculate it, and in certain circumstances it may or may not exist, just like in 1D for single variable functions. So for a function of two variables, the notation for writing down a limit, we say that the limit as x and y approach the point x naught y naught of some function of two variables, f of x, y, is equal to L if the limit exists. So we say that the limit is equal to L. And if the limit does not exist, we just say that the limit does not exist, or DNE. And just like for single variable functions, the limit may or may not exist for any given multivariable function. For functions of three variables, it's the same idea. We say that the limit as x, y, and z approach the point x naught, y naught, z naught of some multivariable function of three variables is equal to some value L if along every single possible path of approach to the point x naught, y naught, z naught, the value of this limit is approaching the same value L, or it could also not exist, in which case the limit would not exist. We just say DNE. This DNE stands for does not exist. And you can extend this concept in the definition that we're about to talk about in general for any function of any number of variables. But in this lecture, we'll just kind of focus on functions of two and three variables. So we need a way of generalizing the concept of limit from a single variable function to multivariable functions. So let's do a little bit of review here, and we'll review limits of single variable functions. is from, say, Calculus 1 class. For a single variable function f of x, we say the limit exists as we approach a point x naught, where the limit as x goes to x naught of f of x is equal to L if the following statement holds. If for any epsilon, so any positive epsilon, we can find a positive delta such that if x is within delta of x naught, but not necessarily equal to x naught, then the distance between f of x and the value L, the limit of the function, remains less than epsilon. So this is the exact mathematical definition of the limit, and you can find this really in any calculus textbook. Now, pictorially speaking, in pictures, this has a very, very nice interpretation. What this means is that we have some value that we're calling L. I'll draw this in blue right here. And then at the point that we're talking about the limit at, x naught, this definition is saying the following. It's basically saying that if this is our function right here, say, and this value L is the limit value of the function, it's saying that no matter how close you get to the function, or no matter how close you get to this limit value, so this is L right here, this line is L plus epsilon, L minus epsilon. This is saying no matter how small this epsilon is, no matter how close you get to this limit L, you can always find what's called a delta, or a delta region in the domain of the function that traps the function inside of a box. This is the box right here. So say x naught plus delta x naught minus delta. So no matter how close you want to get to the limit in the range of the function, you can always find a region in the domain that traps the function inside this box. Right? You can kind of visualize as epsilon gets smaller and smaller and smaller, this box is going to be getting smaller and smaller and smaller as well. But if the limit exists, this will always happen. You'll always be able to kind of zoom in and have the function essentially approaching this value L and staying trapped inside this box right here. Now, what's nice about this is that this definition directly extends to multivariable functions, almost word for word. And we'll see that in 1 second. So this is the from Calculus 1 class, the exact mathematical definition of the limit. the definition for multivariable functions is very, very similar. We use what's called, instead of the absolute value, though, we need a different way of determining distance for the between points in the domain of our function. So we do this with what's called the concept of a norm, or a distance function. So specifically, we're going to be using what's called the 2 norm. Which is the radius of either a circle or a sphere around any point. So you'll remember that we describe points in multivariable spaces using vectors. Say in 2D, a point in 2D is given by a vector x1, x2. In 3D, a point is given by a vector with 3 components, an x component, a y component, and a z component. And you'll remember that the distance between 2 points, let's say the distance between, say, a point u, I'll just do it in 2D. U is u1, u2. And v is v1, v2. We can use the norm to define the distance between these 2 points. So for any vector, the 2 norm is just the square root of each component squared, added together. Or you'll remember this is the same thing as the square root of the dot product between a vector and itself. Remember that the dot product between 2 vectors, any 2 vectors, is the sum of the components, each individual component multiplied together, and then added. This is all. These calculations are in 2D, but this formula and this idea generally applies to 3D as well. So we'll talk a little bit more about the dot product a little bit later, because it's going to come up this specifically when we talk about the directional derivative and using the chain rule, defining the chain rule for multivariable functions. But the main thing to take away from this is that the distance between 2 vectors or 2 points in any dimensional space is always going to be the norm, or the length of the vector where the points are subtracted from one another. Or so in 2D, this is going to be the square root of, say, u1 minus v1 squared plus u2 minus v2 squared. So to get like a picture of this, you can sort of draw out these 2 vectors. Call this vector right here u, the vector u1, u2. And this vector right here, the vector v, is v1, v2. And then we know that the vector u minus v is going to be equal to this, the vector going between those 2 points. So the distance between these 2 points going from here to here, is exactly this, the square root of the difference of each the x component squared and the y component squared. So this distance is the norm of u, this distance is the norm of v, the length of v, and the length of this distance right here is the norm of the vector u minus v. So this idea is very, very important to going through and defining how to take the limit of a multivariable function. So again, I'm going to write down this definition for a function of 2 variables, but it extends for functions of 3 variables or any other number of variables. And you'll remember that the limit as the vector x goes to x naught, or x goes to x naught, of f of x, notationally speaking, is the same thing as saying what we said before. The limit as xy go to the point x naught y naught of f of xy equals L. This is the notation for how we write down a given limit of a function of 2 variables. But this formula, you can see, is general. This expression is general. It could apply for a function of 3 variables or 4 variables. And all of the limit definition also extends, which is kind of a neat idea. So we say that for any epsilon greater than 0, we can find a delta greater than 0 such that the following is true. Say if the distance between x and x naught, this is the norm of this vector, is less than delta, or within delta, so if you're close enough to x naught, then the value of the function f of x minus the limit is within epsilon. So the distance between the value of the function and the proposed limit is less than epsilon as long as you're close enough to the point x naught. That's exactly what this is saying. Another way of writing this, and this actually is general. It holds for functions of any number of variables, and it allows you to define the limit for functions of any number of variables. But for 2 variable functions, right? What this is saying is it's saying that if the square root of x minus x naught squared plus y minus y naught squared, if this is less than delta, then f of xy minus L is less than epsilon. And our interpretation, again, is very, 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 very similar, if not exactly the same idea to how we interpret this for functions of just one a single variable. Specifically, this is saying that at any point x naught with the x naught coordinate here, the x coordinate here, and the y coordinate here as y naught, for any value of epsilon, no matter how small you want to make that value of epsilon, you can find a region around the point x naught, sometimes called a delta region. So this circle that I've just drawn is a circle of radius delta, is saying that for any value of epsilon, no matter how small you want to make that value of epsilon, you can find a value delta such that within this delta region, so if you're inside this region right here, then the value of the function in this region minus the limit is always going to be less than epsilon. So the function is within epsilon of the limit. So you can think of it as the smaller epsilon gets, the smaller this region is going to get. But if the limit is existing, that means that the function is approaching the value of the limit. So essentially, no matter how close you want to get to the limit, you can always find a region around the point where the function stays within epsilon of the value of the limit. So it's saying that the function is getting closer and closer and closer to the value of the limit in this region. And this idea extends again to 3D functions or any number of variable, a function of any number of variables. But the idea is that this is what it means to have a limit. And exactly mathematically, we make a definition for the limit of a function. So let's see what this means for some examples. Because just like for single variable functions in single variable calculus, we're going to see that the limit may or may not exist. One of the main properties that we have for the limit is that it's path independent. And what that means is that if it exists, it's going to be the same value. It has to be the same value along any path. So let's say this is a point x naught in 2D. Right, if you have, say, one path right here of approach, and you have some other possibly very different path of approach, path 2, the limit, if it exists, has to be the same along both the paths, and if it's not the same, then the limit doesn't exist at the point. It's very analogous to the case of, say, if you have a function whose limit does not exist at a point in 1D, like a piecewise function that, say, maybe looks like this, and is this value right here. Right, the limit of this function doesn't exist at this point because the limit from the left is not equal to the limit from the right. The limit from the left is this value, and the limit from the right is this value right here. So the limit of this function does not exist. We have this exact same, this is kind of this statement before multivariable functions. So we're going to see that one way of, say, showing that a limit does not exist for a specific function at a point is to find two separate paths of approach that give different values for the limit along those paths. This is going to be one big idea. We can call this property 1 maybe. Another property that's interesting to point out is that you cannot use L'Hopital's rule for multivariable functions. So there is no L'Hopital's rule for functions of more than one variable. It does work for functions of single variable functions, as you hopefully saw in either a Calculus 2 or a Calculus 3 course at some point. But the idea is that it does not work for functions f of x, y, or f of x, y, z, etc. So this is going to be a potential problem for us. We have to kind of rely on either algebraic or other simplification methods to investigate whether a limit does or does not exist. You can still use L'Hopital's rule for doing indeterminate forms, limits of single variable functions, but we're going to see that it's not possible to do for multivariable functions. So let's look at kind of a very common example of a function whose limit does not exist. And this is the function f of xy is equal to x squared minus y squared over x squared plus y squared. So if you look for the limit at the origin, you run into a problem, because this is, if you just try to directly just plug into this expression, you'll end up getting 0 over 0, which is an indeterminate form. And it turns out that this limit, the limit of this function, just does not exist. It doesn't exist at the origin. To kind of see this a little bit better, we can do a graph of the function, either in GeoGebra, or I'm going to use my Python code. I'll open that up right now. So this is what the graph of this function looks like. And you see very clearly that there's some weird stuff going on at the origin. Looks like the function is nice and smooth everywhere except for at the origin. Let me actually change the color scheme a little bit to make it look a little bit better. We want the highest values to be the red values and the lowest values to be the blue values. So you can clearly see that as you approach the origin, as you get closer and closer and closer to the origin, the value of the function is approaching different points, or approaching different values. I've plotted the surface plot along with a density plot and the contour curves, the level curves of the function down here, so you can see very clearly what's happening. That along lines, the value of the function is constant, and it's a different value no matter any path you choose to approach that origin. So I'll open up both the density plot and the contour plot in the window, and we'll kind of talk about that. I'll open up the density plot right here of this function, along with a contour plot of this function. So you see that no matter what path you choose to approach, say you approach along this line right here, say, call this path 1. Now, along this path 1 right here, the value of the function is around, feels like it's around whatever this value is right here, that color. So it looks like it's around 0.3 or so. And sure enough, if you look at the contour plot of the function, or the contour lines, this is exactly the case, that this path right here corresponds to a value of the function at around 0.3. The limit along this path is 0.3, but if you say move a little bit over, you move to this path right here. Make it yellow so you can see it better on the density plot. The limit of the function along this path, call it path 2, has a value of around negative 0.3, which exactly corresponds to this one right around here, which is exactly around negative 0.3. So the idea is that there are multiple paths here that as we approach the same point, the exact same point, which is the origin, right, there are multiple paths that you get a different limit for, and because of that, the limit of this function just does not exist. It can't exist. Now you can see this without looking at the plot by doing the z traces of this function, or the contour, the contour curves for the function. So if you say fix various values of c, and you look at the shape of the contour curves, right, those contour curves are going to exactly be given by, you end up getting that, it's going to be these straight lines right here. So if we kind of do that, we can do that down below to kind of show you how you don't actually need the plots to do this. If you say fix z equals c for different values of c, you get that the contour curves are going to be curves of the form x squared minus y squared over x squared plus y squared is equal to c. And we can rewrite this as x squared minus y squared is equal to x squared plus y squared times c. Which can be rewritten as x squared times one minus c and it's going to be minus 1 plus c times y squared equals 0. And lastly, this is the same thing as y squared is equal to 1 minus c over 1 plus c x squared. And if we take the square root of both sides, that means that the absolute value of y is equal to the absolute value of 1 minus c over 1 plus c times the absolute value of x. So this is going to be this is the shape of our contour lines, or our level curves for this function. For any given value of c in the range of the function, this is what the level curves are going to look like. And this is exactly what we're seeing. So like say for the value c equals 0.9 here, right? The level curve that you get is exactly this curve right here, this curve right here, this curve right here, and this curve right here. This is exactly this expression, or this curve right here, for the value c equals 0.9. It's the level curves for this function for c equals 0.9. And the idea here is that you're seeing that these curves are giving you for multiple different curves that go to the same point. They intersect the same point, but have different values of c. If you change c to say c equals 0.6 right here, the level curve that you're going to get is going to be this line, this line, this line, and this line right here. Those are the level curves corresponding to c equals 0.6. And because you have two separate level curves that are intersecting at the same point but have different values of c, the limit can't exist, because you have two different possible paths of approach that are giving you different values for the limit. It's completely analogous to how in 1D the limit doesn't exist if the limit from the left is not equal to the limit from the right. That's why this is a really good example of a function whose limit does not exist. And there are quite a few other examples as well. For instance, just do another limit as we go to the origin. We'll look at the function x to the fourth minus y squared over x squared plus x to the fourth plus y squared. So we go through and look at this again. We'll look at the level curves. That's all. Alright, when we fix value of the function z equals c, so the output is equal to c, x to the fourth minus y squared over x to the fourth plus y squared is equal to c. We can rewrite this as x to the fourth minus y squared is equal to c times x to the fourth plus y squared. Can rewrite this a little bit as, by subtracting c x to the fourth, 1 minus c times x to the fourth is equal to minus 1 plus c times y squared is equal to 0. So we get the equation y squared is equal to 1 minus c over 1 plus c and then times x to the fourth. Or taking the square root of both sides, it says that the absolute value of y is equal to absolute value of 1 minus c over 1 plus c x squared. And take the square root of both sides. So the level curves of this function look exactly like this. This is what the level curves, the shape of the level curves is. And what that means then is that for any given value of c, say for example c equals 1/2, say, or any other possible value of c, that the shape of the level curves are going to look like this. So for any value of c in the range, you're going to have a parabola opening up, and also parabola opening down as the level curve for this function for a fixed value of c. And for different values of c, we'll say that this right here is c1. Say you have some other value of c. Okay, this is c2. You have the same sort of picture right here, where you're still going to the same point right here. So if C1 and C2 in general are not equal to one another, and this means we have multiple different, in this case, parabolic paths, where the value of the function is different, but it's going to the same point, that the point's kind of overlapping. So that this limit can't exist. It doesn't exist just based on this simple level curve analysis. And to see this, we can go through and use our graphing program again, our plotting program. So if I run the Python code, take a second to run. And we kind of look at the image that we get when we do the Python plot here. This is the plot of the graph of this function. And we see that if we rotate this to see the graph, it looks very, very similar to the other graph. In that, at the origin, right, there's a problem. There's just it's like a jump almost at the origin, right, where the level curves of this function are behaving exactly like we predicted from our level curve analysis. And at the origin right here, it's kind of like a pinch, right, just like before, where there are different level curves, and along each one of these different level curves, the value of the function is different. But they're all going to the same point. So that we have this problem of multi-valuedness at the origin. At this point, we're trying to take the limit. And you can see that's directly observed in these level curves. These level curves that we found are completely predicted by our level curve analysis, and the limit cannot exist at that point. So these are two very, very good examples of when sometimes the limit doesn't exist at a point, and you have to keep that in mind when you're going through and doing calculations, because it's very important to kind of know what it is you're dealing with. Luckily though, for many functions and many of the functions that we're going to talk about in our examples, the limit will exist, and the functions will be relatively nice. So let's kind of change our what we're thinking about and look at some functions with nice limits and try to figure out how to evaluate the limit, if it's possible to evaluate the limit. That's what we're going to be talking about next. So when the limit does exist, we have a number of different nice limit laws, limit rules that we can use, and we can actually prove using the mathematical definition of the limit. These limit rules are very, very similar to the limit rules in 1D. So I'm going to write down, this is another one of our properties. So I'm going to write down the properties for functions of 2 variables, but these properties directly extend to functions of 3 or 4 or any number of variables as well. So we'll end up using them for multiple different types of functions as we move along in the course. But the first main rule is the sum/difference rule. And this just states that if 2 limits exist, so we're gonna assume for all of these properties that, say, the limit as xy goes to the point x0, y0 of f of x is equal to L, say, and we're going to assume that the limit as xy goes to x0, y0 of some function g of x is equal to some other value, we'll say m. So the sum difference rule says that we can, if we take the limit as xy goes to x naught y naught of f of xy plus or minus g of xy, like you're taking the limit of the sum or difference of two functions, this limit is going to be equal to the limit of the first function plus or minus the limit of the second function, whatever you have. So this is a big rule in terms of computation, and all of these rules, by the way, can be proved using the definition that we gave before. I won't be going over the proof in this lecture video, but the idea is that we're going to be using these for helping us simplify limit computations when it's possible to do so. So the next limit law, or limit rule, is the constant multiple rule. It says that the limit as you approach a point of some, we'll say k is a constant, k is a constant real number, limit of k times some function is the same thing as k times the individual limit of the function, if that limit exists. This is for any constant k. You can say that a constant multiple passes through the limit. So the third is the product limit rule. That's that if you have the limit of the product of two functions, multivariable functions, the limit of this product is the same thing as the product of the individual limits. You have the next one is called the quotient limit rule. Which says that the limit as you go to a point of the quotient of two multivariable functions is just going to be equal to the limit of the top function over the limit of the bottom function. This is, again, assuming that m is non-zero. And this just guarantees that we're not dividing by zero. So as long as the limit of f and g exist and the m is non-zero, you can say that the limit of the quotient of f over g is just going to be equal to L over m. And the last two are related to different powers and roots of a function f. So let's say, for instance, this is going to be the power limit law. If you're taking the limit of, say, the function f raised to the n power, where we'll say that n is a positive integer, the limit as xy goes to x naught y naught of some function of x and y raised to the power n is going to be equal to just the limit of f raised to the power n. And similarly, the root rule, or the root limit law, is the exact same statement, only for the root, the nth root. The limit as xy goes to the point x naught y naught of f of xy to the nth root of the power 1 over n is equal to L to the 1 over n. And now it is important to specify that n is a positive integer, and if n is even, right, we have to assume that L also has to be greater than 0 in order for this to hold, because you can't be taking the an even root of a negative number in real calculus, because you won't get a real number. So that's an important specification. But the idea is that these 6 rules essentially comprise, right, all of the calculation tools that we need for evaluating the limit when the limit does exist, if the limit does exist. We've seen 2 example functions for which the limit does not exist, but there are also many good functions that we can use these limit rules for. And these rules greatly help us as we're going through and doing limit calculations for functions where the limit does in fact exist. So we'll do a couple examples both for 2D functions and 3D functions right now, just to kind of see how to use these. I'm going to take the limit to a function of 3 variables. Actually, I'll stick with a function of 2 variables for now. All of these laws apply for functions of 3 variables as well. Going from as xy versus the point 0, 1, the function x minus xy plus 3 over x squared times y plus 5xy minus y cubed. So we can use the quotient limit law and then the sum limit law on each individual numerator and denominator. The quotient limit law says that this is going to be the limit of the numerator divided by the limit of the denominator provided that the denominator limit is non-zero. And then you can use the sum limit law. I'm not going to keep writing this limit, but you do the sum limit law to get each one of these individual limits. And essentially this ends up reducing down to then just being 0. The limit as xy goes to 0, 1 of x is 0 minus 0 times 1 plus 3 divided by 0 squared times 1. You have x squared times y plus 5 times 0 times 1 minus y cubed, which is just 1 cubed. This entire thing then is going to be 3 divided by negative 1, or negative 3, And sure enough, that's the value of the limit of this function. So this function approaches -3 as you go to the point 0, 1. This is just a straightforward, quick application of how we can kind of show this limiting process. So we'll do another example. We'll do the limit as x comma y goes to the point 3 comma -4 of the square root of x squared plus y squared. This is going to be the same thing as, well, we can use the root limit law first. This will be the limit as xy goes to 3 comma -4 of x squared plus y squared, all to the 1/2. This is applying the root limit law, and then you have the sum limit law and the power limit law you can apply. And what happens is you end up getting this is exactly the same thing as 3 squared plus -4 squared to the 1/2, or the square root of 9 plus 16, which is the square root of 25, or 5. So these are two relatively straightforward examples of applying these limit laws. Now there are certainly other more complicated scenarios that could definitely arise. For instance, you may have to do some form of algebraic simplification, or other type of simplification, trigonometric simplification, before you can directly apply the limit laws. I'll give you a very good example of this in the next example. So we'll do. Consider the example, the limit as xy goes to 0, 0, x squared minus xy over the square root of x minus the square root of y. You can't directly apply those limit laws to this, because if you try and do this, the denominator here is 0. The numerator is also 0, so this is, again, it's an indeterminate form, which might make you think that this limit does not exist, but it turns out that would actually be wrong. This limit does exist. There's a way that we can algebraically simplify it and make it look nice. It's, in some sense, it's very similar to the concept of a removable singularity from calculus 1. So you can use algebra to kind of simplify this, and the way that we do that is by cleverly kind of getting rid of these square roots in the denominator, and noticing that this kind of factors nicely. Specifically, right, if we multiply by the reciprocal, square root of x plus the square root of y over square root of x plus the square root of y. Right, this is not changing our function at all. This is the same thing as multiplying by 1. So we're not changing the limit that we're calculating here. We're still this limit is still the same limit that we're trying to calculate, L. But doing this ends up simplifying this a lot. We get the limit as xy goes to the point 0, 0. X squared minus xy is the same thing as x times x minus y. It's still divided by square root of x minus the square root of y. And then now we have the square root of x plus the square root of y up here in the numerator. and square root of x plus the square root of y down here in the denominator. So it looks like it's more complicated, but we'll see that this simplifies very, very nicely. You have x times x minus y still, square root of x plus square root of y. When we FOIL this out, do the multiplication out in the denominator, this is going to become this times this, which is just x. And the middle terms cancel. And when you do the last multiplication here, you have to do this negative square root of y times square root of y gives you negative y right here. And notice that what this gives us is exactly a very, very nice cancellation. We get that x minus y divided by x minus y is 1. So the limit that we were originally looking for, remember this is just the limit that we were originally looking for, was the limit as xy goes to 0, 0 of x squared minus xy over square root of x minus square root of y. This is the same thing as the limit of x times the square root of x plus the square root of y, which is just equal to, from our limit laws, now we can apply the product limit law, and then the sum limit law, and then the power limit, or the root limit law, to get that this is going to be the same thing as 0 times 0 plus 0, or 0. So we've effectively determined that the limit of this function is in fact equal to 0. So you definitely want to be careful of things like this, right? Sometimes, even though it looks like the limit may not exist, you can go through and show that this limit does not exist, or that the limit does exist, even if you think that it may not exist. So it's very, very important to look at things like this. And let's take a second to kind of plot this out and verify that this does in fact make sense for this function. Just want to go into the Python window and we'll enter in this function, which is x squared minus xy over the square root of x minus the square root of y. And we'll go from go from 0 to 10. And sure enough, you can see that this function, as you approach 0 on the domain of this function is the first quadrant, and inside this domain, as you approach 0 here from both sides, and from any direction at all, this function is smooth and it's approaching 0 as you go to that point right there. And you can also show this, like I said before, using level curves. So actually going through and doing the level curves for this function. So this is a very good example. So just because you have an indeterminate form, it doesn't mean that the limit does not exist. Right? There are other things in many other types of examples that you could possibly consider and see as well. But the idea here is that this is a very good example. Another technique that's very useful is what's called synthetic division. Right? So factoring, synthetic division. There are so many different useful kind of algebraic techniques that we can use to possibly simplify functions if we have to, and simplify the calculation of limits if we have to. But sometimes it's important to do that. Whenever you get an indeterminate form like that, the limit may actually exist if you can simplify that both either the numerator or the denominator. So let's do an example of synthetic division, just to kind of show that there are multiple different techniques here that you can kind of apply. But you really want to become remember some of your techniques from algebra and from specifically a calculus 1 class that were very useful. So let's do, say, the limit as xy goes to 0 of x cubed minus xy squared plus y x squared minus y cubed over x plus y. Again, this, if you just directly try and plug in, you get 0 over 0, which is an indeterminate form. So you might think this limit doesn't exist, but it turns out that we can use a method from algebra called synthetic division, or division of polynomials, to simplify this. This is like long division of polynomials. So if you remember how to do long division, hopefully, from either a pre-calculus course or from an arithmetic course, we can do this with polynomials. Specifically, if you have dividing by the polynomial x plus y, and we're dividing the polynomial x cubed plus y times x squared minus y squared times x minus y cubed. And this works out exactly like normal division does for normal, you can say real numbers. But now what we're doing is we're kind of treating the powers of x as our individual placeholders for coefficients. So specifically, this function right here goes into this polynomial x squared times. You're trying to get rid of the highest order terms in x here. So specifically, if I multiply x squared by this polynomial and subtract, I end up getting x squared times x is x cubed. Then x squared times y is y times x squared. So the remainder for this first division is actually pretty nice. It ends up giving us x cubed minus x cubed cancels out. Y times x squared also cancel out. And what we're left with for the remainder is just negative y squared x minus y cubed. So again, we want to do the next highest order, so we got to figure out what we have to multiply this by to get rid of this x term right here, so this negative y squared x, that's going to be exactly multiplying by this negative y squared. Because when I multiply by negative y squared, I get negative y squared times x. And then also what's nice is that I get negative y squared times y is negative y cubed. So when I subtract out this, the result after doing this division, these two terms cancel out and these two terms cancel out, which actually give us a remainder of 0. Which means that this polynomial right here is really, it's the same thing as the following. It's the same thing as, so what we've just shown is that the polynomial x plus y divides into the polynomial x cubed minus xy squared plus yx squared minus y cubed evenly. Specifically, this numerator is equal to x plus y times x squared minus y squared with a remainder of 0. Which allows us to simplify this, because x plus y divided by x plus y is 1. So the limit of this limit as we go to 0, 0 is the same thing as the limit x squared minus y squared as we go to 0, 0, which is just from our limit laws, 0 minus 0, which is equal to 0. So this is an example showing how you can use synthetic division and really any other algebraic technique that might be useful to use our limit laws and figure out the limits of specific functions. This is a very, very, very nice and kind of powerful method. And you can see that all of these limit laws are very powerful. They allow you to, if you can simplify your function and down to a point where you can apply the limit laws, you can very easily go through and get the value of a limit. So the last thing we're going to talk about today is the definition of continuity, or a continuous function. And what's nice is that once you're okay with taking the limit, and whether a limit exists or doesn't exist, the definition of continuity follows directly from the definition of a limit. Specifically, we say that a multivariable function is continuous at a point x naught if its limit exists at the point that's the first thing. It has to be true. And we have to also have that the value of the function is equal to the limit at the point. So notationally speaking, for a general function, you say that the limit as x goes to x naught of f of x is equal to the value of f at x naught. In 2D, this is the same thing as saying the limit as xy goes to the point x naught, y naught of f of xy is equal to f of x naught, y naught, or say, in 3D the notation is similar. You say that the limit as x, y, z goes to x naught, y naught, z naught of f of x, y, z. This is equal to f of x naught, y naught, z naught. So it comes directly from the concept of the limit that we're talking about. So we say that a function is continuous if the limit exists at that point, and then also the value of the function is identical to the value of the limit. It's really the same sort of idea as in single variable calculus, and it depends, directly on this definition of the limit and the idea of the limit. So this is a very, very nice concept, and it turns out that we have a final kind of general property that's very, very nice for the composition of continuous functions, and we'll use this a lot as we kind of going forward. So first I want to kind of talk about what a composition is for a multivariable function. So say that the composition of multivariable functions is just like composition for multivariable functions of a single variable. It's a little bit more complicated. So let's say, for instance, we have some function, we'll call it w is equal to f of xy, but then you also have that x is equal to some function g of uv, and y is also equal to some function h of uv. You can say that w is then also equal to a function of u and v. Specifically, it's the function when you plug in g of uv for x and h of uv for y. So for example, let's just take a specific example. You could say, let's say f of xy is the function x squared minus y squared, and then maybe x is equal to, say, uv, u times v, and y is equal to e to the u times v. Or we'll do e to the u plus v, just to make it a little bit different. So if w is equal to f of xy, then w, the composition as a function of u and v, is going to be uv squared minus y squared, which is e to the u plus v. Right, so this is how w squared. This is how w depends on u and v in this compositional relationship. Right, so in general, one of the things that you wanna use when you're dealing with compositions of multivariable functions like this is what's called the tree of dependence, also sometimes called the chain of dependence. And this just kind of gives you an idea of how everything depends on everything else. So if you say have that w is equal to a function of x and y, w is the top of the tree, it then depends on x and on y, and then if x and y themselves are both functions of u and v, so x is some g of uv and y is some h of uv, that means that x depends on u and on v, and y also depends on u and on v. So this is the tree or chain of dependence for this composition. But this is going to be a very, very big thing for us, especially when we go through and talk about what's called the multivariable chain rule. So this is just what it looks like for a function of two variables, but you can kind of extrapolate this and see that you can also do this for functions of three variables or any more variables, which is a very, very useful thing to consider. So the main property here that we have is that if we have a continuous function or a composition of continuous functions, so let's say f, g, and h are continuous, if you take, say, the limit, this is the final property that we have for limits slash, it's really limits of continuous functions. I should say the final computational property that we have. If you take the limit of a composition like this, as say uv goes to u naught v naught, this is the composition f of g of uv h of uv. If these functions are all continuous functions, so the limit of all the functions exists, so f is continuous, g is continuous, and h is continuous, this is the same thing as f of the limit of as uv goes to u naught v naught, so it's the same thing as f of the limit of g, and then the limit of h. Which, if g and h are both continuous functions as well, this is the same thing as f of g of u naught v naught h of u naught v naught. So if you have a composition of continuous functions, you can take the limit and actually bring the limit inside as you take the limit. So this is a very, very useful computational property that we see a lot, and we're going to use a lot when we're going through and evaluating limits. And what we'll end the lecture on is going to be this last, so that we have one more property. This is called the extreme value theorem. This is for continuous functions. And this says the following. It says that if f is continuous, on some closed bounded domain, then it attains absolute maximum value on the domain. We'll say absolute maximum and minimum on the domain. and this is the last big property that we'll see in many different examples as we kind of go throughout the course. So you can use the ideas that we've been talking about to prove this, but the idea is that this will be an important theorem when we start talking about optimization of multivariable functions and maximizing and minimizing multivariable functions. But this will conclude it for the lecture today. Thank you very much for tuning in, and I hope you learned something.